We'll present our work beyond sight towards cognitive alignment in large vision language models via enriched visual knowledge. As shown in the figure, even advanced models like GPT-4o and LVL fail to identify well-known landmarks from images, despite accurately describing them when provided with text-only prompts. We call this gap cognitive misalignment. The vision encoder speaks a dialect the language model does not fully understand. Our work asks, how do these problems emerge? How well do these models truly understand what they see? We quantify the vision encoder's knowledge with two scores, a similarity score to the true label and its rank among all labels. We then sort the entire dataset by these metrics and carve out 4 equal-sized splits. The top-ranked images form the high discrimination set. Those with the highest absolute similarity form the high similarity set. At the other extreme, low scores on both metrics give us the low clarity selection. A random slice serves as our baseline, BRS. The TS&E plots on the right make the contrast visual. In HDS, points from the same class spread widely, capturing fine intra-class detail. HSS forms tight, well-separated clusters. LCS, by contrast, collapses into a fuzzy cloud, signaling poor discrimination. We fine-tune LAVE 1.5 on our curated subset. After training, GPT-4o grades every test answer as strongly known, known, weakly unknown, or unknown. The known ratio, strongly known plus known, is our accuracy. A quick look at these splits reveals 3 insights. First, the HDS and HSS groups, what we call vision encoder known data, consistently reduce misalignment and boost accuracy. Second, the LCS group, our vision encoder unknown data, actually makes things worse. Third, pouring in more vision encoder unknown images produces sharply diminishing returns. In other words, better images matter far more than more images. Why does the gap persist? Standard adapters treat visual tokens like generic words. They overlook discriminative cues that an LLM needs to nail an entity's identity. These findings hint at the real challenge. The adapter should pass tokens that already capture the cues the LLM reasons over. In other words, we need a shared cognitive space. To build such tokens, we extend our dataset with a multi-granularity annotation pipeline. Each landmark now carries a coarse hierarchical label, tower, church, lake, plus fine-grained entity tags. This layered signal tells the model what an object is and why it looks unique, matching the way the LLM organizes concepts. Building on our annotated data, we introduce the Entity-Enhanced Cognitive Alignment, EECA. Picture the vision encoder as 2 lenses, a wide angle for the full scene and a zoom that grabs crisp patches. For each patch, we score its cosine similarity to every textual entity, sparsify those scores, and use them as soft weights. The weighted sum gives 1 tidy entity grouped vector per entity. Then we add 2 forces. Entity-aware contrastive loss pulls each vector toward its matching text entity and nudges it away from the rest. Hierarchical loss keeps the pooled global embedding tied to its course class, like tower. Based on this supervision, EECA turns raw pixels into tokens the language model can reason over, literally opening its eyes to the image. Here is one item from our multi-granularity landmark dataset. On the left, you see the image, a brief QA conversation, and the hierarchical tags and entities we add with GPT-4o. On the right is our evaluation prompt to GPT-4o to label each answer for every test image. Now we examine the importance of each component inside EECA. In the left table, you see an ablation study. Feeding the model 50K carefully selected vision encoder known samples lifts accuracy at once. Adding a high-resolution branch without new supervision actually hurts. The extra tokens are noise. But once we pair that branch with our entity-aware and hierarchical losses, the same detail becomes signal, and accuracy climbs to its best level. Next, we ask whether these gains hold on every kind of data. The right table answers yes. On vision encoder known splits, the 2 losses provide most of the boost, while on the vision encoder unknown split, the high-resolution branch does the heavy lifting. Together, they show that EECA adapts smoothly to both familiar and unfamiliar images. Please refer to our paper for more technical details. Thank you for watching.